All right, just for sake of the recording, I'm going to take 1 minute and we're going to go, hey, -5, infinity, -5, D, N, E, 1, 1, 4, 1, -2, -2, D, N, E, -2. Check your answers, and now we're moving on. Kabam. Okay. Today's learning target, continuity. Moving on. So, definition of continuity, the limit as x approaches a of f of x equals some number which equals the same value as the function f of a. All right, that's your definition of continuity. The 3 conditions that are required to be true that say the same thing basically as this, like this and this are pretty much interchangeable. Is the function defined? Does the limit exist? Do they equal each other? So if those 3 things are true, the function is continuous. How do you know just by looking at a function if it's continuous? If you can draw the function without lifting up your pencil, then it's continuous. If you have to lift up your pencil, it's discontinuous. Now, I always have students, and I kind of like nip this in the bud right off the bat. So, like, I always have students who, come on, why is it not going? No. One moment. What is it? I think I drew over here. Okay. So I always have students who like do this kind of a thing and say, "Oh, look, I drew without lifting my pencil." Right? Okay. So anyway, but a hole on a real graph doesn't actually look like that. That's what we do to like make it really visual to the reader, like, hey, there's a hole there, right? But in reality, if you actually graph it, the actual graph just looks like that, right? So there's no like actual circle around the spot that's missing. It's just missing, right? It's just empty space. Yeah. So if you can draw the graph without lifting your pencil, then the graph is considered to be continuous. However, I can draw the graph without lifting my pencil is not appropriate justification for saying why a function is continuous. So that's why we actually need the definition of continuity. So that's what we're going to be focusing on today for a big part of the day. So we're going to start with this example. So to the right is the graph of a function of f. State the values of x at which f is discontinuous. Then use the definition of continuity to explain why a discontinuity exists at each x value stated. So just a little thing to point out that I didn't point out first period, and I'm pointing out in the video, okay, is if your function is continuous and you need to prove it's continuous, this is what you write, right? This shows the function is continuous. So if the function's continuous, you can write this nice little 3-way equality here, and that's your proof. Now, you would actually fill in with what the numbers are, right? So the limit as x approaches 2 of f of x is 5, which equals f of 2, right? That would be fine. You need numbers, not just the generic term. But if the function is discontinuous, that's where you break it down into one of these guys, because one of these guys is going to fail. So either it's going to be discontinuous because the function's undefined, or because the limit doesn't exist, or because they don't equal each other. One of those 3 things is going to be your reason for discontinuity. So if you're showing continuous, you use this guy, for sake of the video, this guy, right? If you write that out properly, that proves continuity. If you're showing discontinuity, then it's one of these 3 things failing. Okay. All right, so in your groups, I want you to take 30 seconds and decide which x values have a discontinuity for this graph. Begin. Which group haven't I called on in a while? Apparently I've called on all of you.
Yeah.
I have. I've done a good job of calling on everybody. I'm going to call on this middle group right here. So let's see. Hi, Vishali.
Hello.
How are you doing?
I'm great.
Good. I'm doing good. All right. And You have a lovely dress on today.
Thank you.
You're welcome. So, Vishali, tell me just one x value where you think this function is discontinuous.
Oh,
At x equals 1. Good. What was the tip-off that it was discontinuous at 1?
because
Okay, yeah, that was like really advanced. I was just going to say there's a hole there, right? Okay, good. Does everyone agree that it's discontinuous at 1?
yes.
Okay, so here's what you would have to write. So we're going to write these using the correct wording because you do have to learn this wording. So let's learn how to write some of these answers that require words. So, come on, there we go. So f of x is discontinuous. You can abbreviate discontinuous with this and then just put a dot and then keep going. So f of x is discontinuous at x equals 1 because. You're going to write the word because about 10,000 times this year. So I do B/C for because. So whatever you want to do as long as I know it means because. So f of x is discontinuous at x equals 1 because. Now it's got to be one of 3 things and you check them in order. So Vishali, is the function defined at 1? That's your answer then. So you would say because f of 1 is undefined. Done. Does that make sense? Yes, Faith. You can say not defined, yeah. Anything that implies that. You could say DNE. I learned that WebAssign doesn't let you put in UND, that you have to put DNE even for functions, so I apologize if that messed you up. But if you have a function that is undefined, in the blank there, they want you to type DNE for it.
Is there a difference between undefined and discontinuous?
Normally we say a function is defined or undefined, and we say a limit exists or doesn't exist. So that's traditional mathematical jargon, but it doesn't mean you have to say it. I mean, if you say the function doesn't exist, it's a true statement. So no one's going to take off if you write that. It's really just following tradition. Yeah. All right. So, all right, Luke, since you are speaking, how you doing?
Good.
Your day going okay?
Yeah.
Did you enjoy Connections?
Yeah, it was fun.
Did you sign up on your handbook?
Yes, we did that last time.
Last time? Okay. And was EVN playing today?
Yes.
I didn't get it to come up.
Virgin's View?
I plugged in, connected, put it on the right channel, and I never got any feed.
Yeah, we didn't.
Okay. Okay. All right. Well, that's good to know. Then I will try to get it working before next week. So Luke, sorry to distract. Luke, tell me another x value where this function is discontinuous. At 3. So f, you are correct, is discontinuous at x equals 3 because. All right. So Luke, we're going to walk through the 3 conditions. Number 1, is f of 3 defined? How do you know? Yeah. Right, there's a dot there, right? Okay. Does the limit as x approaches 3 of f of x exist? No. Why not? Not the same for both sides, right? Okay. So that's your reason. You would say because the limit as x approaches 3 of f of x does not exist. Now, if you want to be like a superstar, you would justify why the limit doesn't exist. There are some questions where they're going to make you justify anyway, so might as well just learn how to write it. How do we know this limit doesn't exist? Because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right of f of x. So that's why your limit doesn't exist. Not the same left. Okie dokie. Ryan.
Yes.
Yes. Ryan, tell me an x value where this function is discontinuous.
5.
At 5. How did you know that the function, well, let's just walk through it. I'm just going to write it first. F of x is discontinuous and x equals 5 because, all right, Ryan, is f of 5 defined?
Yes.
How do you know? There's a dot there, good. Does the limit as x approaches 5 exist?
Yes.
Yes, because both sides point to the same spot. So why do we have the discontinuity?
Because the f of 5 and the limit of as x approaches 5 are.
Yes, beautiful. Did you guys hear that? Okay, so how do we write that? We say, is you okay?
Yeah.
Oh, you didn't see the dot? That's been the trend of the day, is not seeing the dots. Okay, because the limit as x approaches 5 of f of x, right? When you're writing LIM, there has to be something next to it. Otherwise, it's just nonsense, right? It's like writing a square root with nothing inside. So you have to have a limit of something. Otherwise, it's just silly. So because the limit as x approaches 5 of f of x does not equal f of 5. All good? All right. Now, if you were doing this problem on a test and you had a whole bunch of space, we would probably make you justify more. Like we would probably say, have you state what is f of 5 and what is the limit as x approaches 5 of f of x. On a graph, it's pretty easy. When you're given a function, it's not quite as easy, and you have no y values, so you wouldn't know anyway because we don't know. We're just guessing, right? We just know they're not there. All right, so we're going to do some now without a graph. And this is going to be for you guys to do in your groups. Are you ready?
Yes.
Ooh, good. I like that. Like,
Woo!
yes, we are ready. Okay, I have 3 problems here. Each of these 3 functions is discontinuous at one value of x. Your job in your group is to figure out what x value the function is discontinuous at and then state why the function is discontinuous there. Your why has to be because the function is undefined, the limit doesn't exist, or they don't equal each other. All right, are you ready? Set, begin. We're going to pause. So for the first one, all right, so for the first one, coming to the front group. So Tarun, what x value like jumped out at you as a possible point of discontinuity?
2.
2. Why 2?
Because you put 2 as x, then on the bottom is 0.
Yes. Anything that makes you divide by 0 is going to be, there's going to be an issue, right? Okay, so that's the thing to investigate is anything that makes you divide by 0. So whenever this isn't a piecewise, it's just a traditional old rational function. So if you plug in a 2, do you get out a function value? No. Now, it doesn't matter if there's a hole there or an asymptote. We don't care because we know f, come on, one moment. There we go. We know f of x is discontinuous at x equals 2 because f of 2 is undefined. Dividing by 0, you're done. Function's undefined, move on. Is that okay? Yeah. All right. All right, so let's move on to B. Tommy, how you doing?
Good.
So what x value did you focus on for B?
0.
0, right? For 2 reasons. One, 0 makes you divide by 0 for this guy right here, right? And it's also the handoff spot. Whenever you have a piecewise function, the number over here, this like handoff spot, can cause a problem, right? You can get like one of like comes in here and then takes off down here or whatever, or you get a hole and a dot or something like that. So this guy is usually the one to take a look at on a piecewise function for discontinuity. But you also want to pay attention to the denominators. In this case, they're the same, so you're good. So let's walk through our 3. So Tommy, is f of 0 defined?
Yeah.
What is it?
1.
1. So f of 0 is 1. So What about the limit? When we have a not equals equals kind of a piecewise, do we use the not equals or the equals for the limit? The not equals, why? Because the entire function is controlled by this guy. This guy right here, what is that? That's literally a dot at the point 0, 1, right? That's all it is. And a dot cannot control a limit. This guy controls the limit. Because this is what's true for every single number on the entire real number line except 0. This is just a dot at 0. So if we find the limit of f of x, so without even knowing like what the limit is, if we plug in a 0 to the top, we get not 0 over 0, which means the limit does not exist, right? So we would say f is discontinuous at x equals 0 because the limit as x approaches 0 does not exist. Now, if we wanted to be superstars, let's just take a moment to review. If I asked you to tell me more specific information about that limit, Tommy, what's going on the graph at 0?
There's a hole.
Are you sure there's a hole? Is there a hole there? Or is there a vertical?
Oh, yeah.
How do you know it's a vertical asymptote, not a hole? Okay, but holes are also division by 0. So there you go. There you go. See, you got this. Okay, not 0 over 0 is what tells you it's a vertical asymptote. When we have a vertical asymptote and you're asked to find the limit, you have to check from the left and the right. Because you got to know, is it doing this or this kind of a thing, right? So for a vertical asymptote, we check left and right of 0. But the good news for this function is this is always what? Positive, because you're over an x squared, right? Which means this guy's doing this thing. So your limit actually approaches infinity. So you could write, because the limit equals infinity if you wanted to. But anyway, all right, that's enough about that. Kirthana, how are you? Good. Did you guys get to letter C? Oh, I haven't even asked, what's under the green boxes? Ooh, what do you think's under the green boxes? Graphs. Graphs. Just so you can see visually. So for this first one, and they're terrible graphs because you can't, it doesn't emphasize the hole. This one, there's a hole, right? This one, hey, this is one of those vertical asymptotes with a dot right there. So you have a vertical asymptote at 0, and then you put a dot right there on the vertical asymptote. It's kind of fun. I like putting dots on vertical asymptotes. All right, and then part C. So, Kirthana. So what x value did you focus on for letter C? 2. So we know it's going to be discontinuous at 2. I'm going to walk through. Let's just, for the heck of it. What's f of 2? F of 2 is 1. So if we were going to do the limit as x approaches 2, would we be using the top or the bottom? Why? But I'm talking about like this, like for this piecewise function, this whole top versus this whole bottom. There we go. Yes. Okay. So we're going to do the limit of this guy. So we do the limit as x approaches 2. All right. What's your favorite F word? Factor. Is it really your favorite F word? Okay. That's awesome. Is it everyone's favorite F word? For real? No? Okay. All right. Yeah, I know. It's fraction, right?
Yeah, totally.
Okay. Or function.
Just fun.
Okay. Or let's see. Fractal, right? You guys do fractals in geometry? No? Okay. Anyway. All right. So factor. I'm glad that this is your favorite F word. So let's factor this.
C x minus 2x plus 1.
Beautiful. I didn't even have to think. All right, so these guys cancel because we're in limit world. So the limit as x approaches 2 of x plus 1 is 3. So f of 2 is 1. The limit is 3. Why is this function discontinuous? Nailed it. Okay, so f of x is discontinuous at x equals 2 because the limit as x approaches 2 of f of x does not equal f of 2. The limit does not equal the function value. So this one has a hole and a dot. A hole and a dot. How are we feeling about these? The discontinuity thing. Because this is on your test. Like, it's a lot on your test. So, wait. Ishan.
Yeah.
Hi.
For B, couldn't you also say like the limit is not equal to the function?
So technically you could, but I prefer to say the limit doesn't exist. And that's why I tell you to go in order. Function, limit, do they equal each other? Because when the limit doesn't exist, then nothing's going to equal it. So it's kind of silly, right? Like, it's saying, like, hey, here's this thing that doesn't exist. Does this equal it? No, nothing can equal it. It literally doesn't exist, right? So nothing can equal something that doesn't exist. So to me, the reason isn't because the function doesn't exist. It's because the limit doesn't exist. Now, if you put the third thing, that the limit doesn't equal the function, it's technically correct. It's just annoying. But it is technically correct, so I would probably take it, but it would make my shoulders go up. So just know, when I'm grading, that I want you to go in order, and if you put the third one for something that's the second, if it's correct, I'll accept it, but now my shoulders are up on grading the rest of your test. Yes?
Oh, I was gonna say, like, if it was on the AP test and you, like, forgot the college board would accept it.
They would. Yeah, it's true. As long as it's true, right? It's true. Okay. Was there, oh, wait. Let's see. Anisha.
Yeah. Wouldn't the limit be infinity for B?
Yes, it is infinity. Yes.
But then that's technically does not exist.
Beautiful. Yes, very good. All right, do not write all of this. Here's what I want you to write. I want you to write removable discontinuity, and I want you to write if the limit exists, the discontinuity is removable. That's all you have to write. We're going to talk about it, but as far as writing goes, you got those two things, life is good. There are 3 types of discontinuity. So there's point, line, and jump. Some call them point, jump, and infinite. There's, whatever. So different ways to say the 3 different types of discontinuity. Basically, point discontinuity means you have a hole in the graph, right? Doesn't matter if there's a dot there or not. If there's a hole in the graph, that's called a point discontinuity because it occurs at a point, right? A jump discontinuity is when you have like one of these piecewise functions where you like start here and then you jump down to there, right? That's called a jump. And then the last kind is infinite or line discontinuity, which just means you have a vertical asymptote, right? Something like that. So 3 discontinuities. You have point, line, and jump. If you have a point discontinuity, it's considered removable. Why is it called removable? Because if you can change one value on your function and make the function continuous, then that discontinuity is called removable. Now, if you don't have to make a whole function, just continuous at that spot. So if you're discontinuous at x equals 5, and you can redefine f of 5 to be some other number, and now all of a sudden you're continuous at 5, that means that that discontinuity was removable. So, and it only works for holes. So the easy way to remember, and the easiest way to justify if a discontinuity is removable or non-removable, is if the limit exists. So if the limit exists, the discontinuity is removable. If the limit does not exist, the discontinuity is non-removable. Right? So where the limit exists, that means there was a hole there, means it's removable. Limit doesn't exist, it means either there was a jump, right? Limit doesn't exist, or there's an asymptote, limit doesn't exist, right? Okay, so if we take a quick peek at these three graphs, I want you to just, as a class, yell out for this one, removable or non-removable? Removable, because the limit exists. For this one, removable or non-removable? Non-removable, the limit does not exist. For this one, removable or non-removable? Removable, because the limit exists. Is that okay? Okay. All right. All right, last example of this, and then we get a little bit of different stuff. So we didn't have a lot of time on piecewise yesterday, so I want to make sure we're really clear on how to find limits of piecewise functions. So I've got another like less than, greater than kind of a piecewise, one of these kinds of things. And I want you as a group to see if you can figure out where this function is discontinuous, but I don't think it's going to be too much trouble to find that x value. And then use the definition of continuity to prove it's discontinuous there. Once you do that, decide if it's removable and explain why or why not. So think carefully. Remember, you're going to start, is f defined at that spot, yes or no? Does the limit exist at that spot, yes or no? Do they equal each other? To check the limit on one of these guys, what are you going to have to check? The left and the right, because it's a different function on the left and the right, so you have to do a left and a righty. All right, get to work, take a minute. All right, we're doing fine. So, let's move to a different group. Oh, wait, except I never called on Megan. So Megan, what x value did you guys focus on? Why -4? Yeah, that's what I like to call the handoff point. Yeah. There's no denominator, so these are never discontinuous on their own. The only place it could be discontinuous is at the handoff point, so the -4, right? Okay. So let's see here. Hi, Emma.
How's it hanging?
It's hanging great. Okay. So Emma, first thing I'm going to ask you, if this was like, say this is a test problem, right? You're sitting here, you're looking at this, you're taking your test, and you think to yourself, I'm going to walk through my 3 conditions, and the first thing I'm going to check is the function defined? And what would be a good thing to write? Not that. Yeah. Let's get this moved up. Let's actually write it. F of -4. Emma, did you use the top part of this piecewise or the bottom part to find f of -4?
The dot is actually on the top function because it's equal to -4.
Beautiful. Okay, did you guys hear that? She said it perfectly. She said, look, we use the top because that's where the equals is, right? That's where the dot's going to go. So you plug into the top, and Emma, what do you get? -13. So is the function defined? Yes. So that's out. What do we need to check then?
You have to check if the limit is the same.
We got to find the limit now. So we're going to do, on our paper, we're going to write the limit as x approaches -4 from the left, and the limit as x approaches -4 from the right. I want to make sure I clarify something because I've seen at least 3 students, which means there's more than 3, who, as soon as they see a left and right-handed limit, they start plugging in numbers close, like -4.1, -3.9. That is only for vertical asymptotes that you do that. That's only vertical asymptotes. All other left and right-handed limits, you just plug in the number. All right? So the only time you're picking something close is when you're doing vertical asymptotes and you want to check the signs. So -4 from the left. So, Faith, would we use the top or the bottom for our -4 from the left? Yeah. Why?
Because it's less than
Beautiful. And what did you get? -13. And then from the right, you use the bottom. What did you get?
7.
So what do you know about the limit?
It doesn't exist.
It doesn't exist, right? So we would say f of x is discontinuous at x equals -4 because the limit does not exist. Good. So last two quick questions on this one. Zuhair, is our discontinuity removable or non-removable? Why? Ask for help. Beautiful. Okay, so this is removable. Oh, non-removable. Thank you. Non-removable for the same reason that it's discontinuous because the limit doesn't exist. All right. Any questions on that one? So we have an interesting topic. We're going to do our brain break though. Well, we have a guest in the room. That's okay. So we'll have our guests in the room while we do our brain break. So this is our first time of doing getting to know you. Sorry, we do a brain break every day. It's just a 1-minute thing. So, all right. So this is our first. So once I can get this back up and running. Oh, wait, just a quick, we've talked about this already. You don't have to write anything down. We've already covered this. I added this slide again because they're going to talk about, there are two more little slides we're just going to mention. So if they ask you about where is tangent, right, or any tangent, secant, cotangent, where are those discontinuous, we've already talked about wherever they're whatever values make the denominator equal to 0, right? So we know cosine is 0 at the pi halves multiples. And again, we don't have to get into the serious set notation with the plus and pi kind of stuff. You can just list off the values and you're fine. All right, we've already talked about that, so let's move on. The only other quick thing I'm going to mention is just talking about the difference between continuity and domain, and then we get into our last topic. When you are asked to state where a function is continuous, so we've been focusing on where it's discontinuous, that's easier, so listing off x values. If you're asked to state continuous, those are intervals, right? Might be all real numbers, might be all numbers except a vertical asymptote, right? Anything like that. It's almost always the exact same as finding the domain of the function. The main time they're not the same is with piecewise. Piecewise, like, always throws a wrench into everything. But for most functions in the world, the domain is the same as the intervals of continuity. All right, so, all right, let's move on. We have one last thing to talk about, and I wish I could make this bigger. That's about as big as I can make it, and it's this guy right here. It's a random topic, and the reason that it goes into this spot is only because you have to do it after you learn continuity. So does anyone know this notation right here, this f of g of x?
Yeah.
What is that? Do we know what we call that? It starts with a C. It's like something you write. You write a composition? Composition! Well done, Jennifer. Okay, yeah, you write a composition. All right, this is a composition of functions. And so what this is saying is, when you do a composition of functions, like f of g of 3, so if we're just in general doing f of g of 3, how would you do this? You'd go inside out. First, you'd find your g of 3, and then whatever you get for that, you plug into the f, right? With limits, it's the same way. So with your limit, you're going to, when you have, how do I say this? This is just fancy talk. So if the limit is b, then the limit of f of g of x is f of b. You're finding the limit of the inside, right? The inside, and then you take that and plug it into the outer function. This is only true if the outer function is continuous there. If the outer function is discontinuous, weird things can happen. Today we're going to do pretty straightforward ones, and then tomorrow we're going to do a few weird ones. So you find the limit, and I wrote like in other words. So the limit of f of g of x is f of the limit of g of x. You do the limit of the inside, and then you plug that into the outer function. Are you ready to try some? Do you need another minute to write? So on the next slide, I'm going to give you 3 sets of graphs. I'm just going to give you a little information. If you can't see them well, feel free to send a scout up to the screen to look better. So, it looks freaky, don't freak out. This first one, this is F, this is H. So the first graph is your outer, the second graph is your inner. This is F, this is H, and the problem says find the limit as x approaches 0 of f of h of x. Remember, you work inside out, all right? This one, limit as x approaches 2 of f of g of x. And then the last one, limit as x approaches negative 2 of h of g of x. So I want you in your groups to take the next 2 minutes or so, discuss these, see what you can come up with for these 3 limits. And I'm just going to kind of sit and see how you do.
Keegan is bad at math.
Oh, thank you. Let's pause. For this first one, this is F, this is H. We're going to start inside out. So we're going to find the limit as x approaches 0, whoops, on our h of x function first, right? All right, so we're looking at this guy. So tell me, what's the limit as x approaches 0 on this function? 0, right? So now you take that 0, right, the limit, and you plug that in, and you say, all right, so now this is 0. What is f of 0? So what is f of 0? Negative 1. Whoop. That's your limit.
Oh.
Okay, so what do? You start with the inside function. So your inside function is h, so you do the limit of the inside function, and then you take whatever you get and you plug it into your outside function. Okay, so you do the limit, it's the limit. It's not what is h of 0, it's the limit as x approaches 0 on h of x.
What was like the thing on the other side where it was like if the limit of g of x equals f of the limit of g of x?
Oh, okay. So this is just kind of writing it in a nutshell, saying, hey, if you're asked, like on this problem, you were asked what's the limit as x approaches 0 of f of h of x, right? So in this case, here it says, hey, the limit as x approaches a of f of g of x is f of the limit as x approaches a of g of x.
Other way of like.
Yeah. So you do the limit of the inside and then plug that into the outside. All right. Okay, so for the next one, because the bell's going to ring, what's the limit as x approaches 2 of g of x? 3. And what is f of 3? 2. It's 2. Does everyone see that?
Yes.
Okay. Last one, a little tricky. What's the limit as x approaches negative 2 of g of x? 0. What's h of 0? So h of 0 is negative 1, except you can't do that because h isn't continuous there. So if you have a function where when you plug it in, it's actually discontinuous, then your limit doesn't exist. Okay? Good work today, guys. All right, so that here ended the lesson, and I'm going to stop the recording.